Hello, everyone, and thanks for joining us. My name is Brian Langelier. I'm a staff member at the CCEM, and today I'll be speaking on the introduction to atom probe tomography. So I've made this talk, as says in the title, right at the introductory level. So if you don't have any familiarity with atom probe but are interested in learning about it, then this talk is for you. If you do have some experience with atom probe, then hopefully you can still pick up on something new. So overall for this talk, I'd like first to kind of introduce the technique, define what atom probe is, and give a few application examples. And then the two main aspects of the atom probe experiment that I'd like to focus on are atom probe sample preparation and data acquisition. To those who know about atom probe know there's a little bit more to a total atom probe experiment than that, but we'll be leaving those topics for a future date. So as an introduction to atom probe, what is atom probe? Well, here's our atom probe at the CCEM. It's a local electrode atom probe, which is the design of all the modern atom probes, really. And the atom probe is a tool, a microanalysis tool like many of the others we have at the CCM, but it differs in a key way. Instead of using an imaging media like photons or electrons to interact with the sample and learn about it, atom probe actually uses the atoms of the sample itself. So to clarify what I mean here, let's say we have our atom probe sample, and like also a material is just a collection of atoms. We don't need to know what they are or their configuration. What atom probe will do is actually pick the material apart, atom by atom. It's a destructive technique, but it's not chaotically destructive. As it does this, and these atoms are leaving the material, we're measuring things about them, and we're identifying them. And then we can use this information once we've finished our kind of data acquisition stage to build an atom by atom reconstruction of that original material that essentially works as an atomic scale 3D model of our original sample. And it's this model that we really use to analyze and solve our material science problems. So how does this whole process actually work? Well, atom probe is able to do this kind of an atom by atom disassembly of material through the process of field evaporation. And this is the tendency of surface atoms to ionize and desorb from a material in the presence of a strong electric field. So since we want to do this disassembly of the material very carefully, what we'll do is we'll take our sample, we'll apply a strong potential to it, a strong electric field, but then what we want to do is either apply a pulsed voltage or a pulsed laser onto the tip of our sample to really just pick off those atoms, ideally one at a time. And as those atoms fly off the material, we measure their position in XY where they impact on our position sensitive detector. We also will be measuring their time of flight. And we'll gather this information for each atom that we'll be picking apart. And then we'll do this again and again at a high rate until we've collected tens or even hundreds or more or millions of atoms. And this will represent, usually a volume of material in the size of, tens to hundreds of nanometers. And so once we've collected all of this data, we then need to move to the next part of the experiment, which is turning that into our reconstruction. Now, what a reconstructed atom probe dataset is essentially a point cloud of atoms, where for each of these atoms, we have its XYZ spatial coordinates, and we have that elemental identity. And in atom probe terms, we define that from a mass to charge ratio. So the XY information we can get from the detector XY hit info. The Z we can actually infer from the evaporation sequence. The atom that evaporated first came from further up in the material than the atom that came off, 10th or 100th. And all of these parameters get put together using various reconstruction algorithms and different methods of spatial calibration, which we can get into later. And then as far as the elemental identity, like I said, we get that from the mass to charge ratio because what we're actually measuring, of course, is the time of flight. And mass and charge of the ions will both be what affects that time of flight. So when we look at our mass spectrum in atom probe, we're going to have peaks at different mass to charge values depending on basically the weight of the atom, the atomic mass, as well as what charge state, 1+ or 2+ or so on that it evaporated in. But we can compare that to known masses of the elements and then put them in given charge states. And since we're looking at the mass, we'll also be able to pick apart different isotopes. So then we can also use the natural abundance of those isotopes to identify the different mass to charge peaks as belonging to different elements or combinations of elements. And so that we can use that to then get an elemental identity from a mass to charge ratio. So once the reconstruction is completed and all put together, we're left with essentially our 3D model. So you can see an example of it here for an intercritically annealed steel, which you can see has a few phases in it. So we've got our reconstruction. I've got the kind of a rendered data set spinning there on the left. We've got our mass spectra below showing all the different peaks of the different isotopes and different charge states, color-coded based on what type of ionic species they belong to. And then I've got some atom maps shown up here to the right. And this is just kind of a very basic analysis that we can do is just by looking, where the atoms are in the sample. Right away with this sample, we can even see a few things. We can see it's got two phases, one that's rich in carbon and manganese, one that's more lean in those elements. We can look and see that molybdenum appears segregated at these interfaces and niobium at these little carbide particles. And then that's really where we get a lot of the information from Atom Probe, is essentially looking at the arrangement of atoms, what they are and where they are. If they're segregated to any areas, if they are forming any features that we can see, and then we can measure the features and so on. And we can really go in depth with this. And the good part about Atom Probe data is once you have this 3D model, there's no need to go back to the actual instrument. You have this online, you can pull it up in the reconstruction software, you can continue to go back, reanalyze it, go through it again, and so on. Because really this 3D model is what you're going to kind of be basing all of your real analysis on. And so just to show kind of a few examples of where we've applied Atom Probe at the CCM, just some quick broad strokes. Now, Atom Probe as a technique kind of has its basis in metallurgy. And we've done a lot of metallurgy-based work at the CCM. One example that really shows what something Atom Probe is really good at, which is looking at clustering and solute segregation within a bulk material. And so you see for the example in the top left, where we've been able to pick out aluminum magnesium clustering during early stage aging of a 6000 series aluminum alloy. We can also see some clustering in the image in the top right due to radiation damage in steel. So in this case, nickel and silicon segregation. We can also view, where solutes are segregating with regards to other surface defects or planar defects within the material, such as interface segregation. As we see here in the bottom left, we're looking at the transformation interface in steel. And picking out, even fine scale segregation that we see here in that graph on the top right, where it shows, even a small amount of manganese segregation, that's about 1 atomic percent, is still quite clearly visible within the Atom Probe data. We can also go beyond just the case of pure metals. In the case to the bottom right, we looked at internal oxidation, alloy 600. So we could see that mixture of metals and oxides. And here really showing a strength of the Atom Probe in being able to render in 3D very fine scale phenomena. So you don't really have to then suffer from projection effects that you might otherwise have, in something like TEM. And so while, we kind of have the basis of Atom Probe again in metals, we expanded to things such as oxides, but even more exotic materials than that. So the image on the left is showing some work, early work done, looking at human bone in collaboration with Dr. Granfield's group. In collaboration with some researchers at the Royal Ontario Museum, we've been looking at minerals and using Atom Probe to study minerals and geology materials is becoming more common nowadays. We can also use the Atom Probe to study, devices and semiconductors. As we see here as an example on the bottom right of a gallium nitride nanowire, where we can see the quantum wells clearly formed by the alternating layers of indium and aluminum within that nanowire. And so really kind of the umbrella of materials that are possible to be studied by Atom Probe is kind of ever increasing. So whereas you have the kind of the basic ideal material being, a relatively pure, nicely conductive crystalline metal, we can get further and further than that. And nowadays, there's lots of work being done to expand, what is possible to analyze with Atom Probe. So this is all well and good, showing some nice examples of applications, but I don't want to get ahead of myself because what we really want to get into here is defining the parts of the atom probe experiment. So just to go over it then, the atom probe experiment, we basically, have our starting material, varies or whatever it might be, and we'll need to make our sample out of it. And I'll be speaking of, a lot of the requirements that we need for making an atom probe sample in a minute. Once we have that sample, then we can begin the data acquisition stage that's the field evaporation step. And that's the step that's actually using the atom probe tool itself. After that, we then do that reconstruction phase. And so that's the overall atom probe experiment before you even really start analyzing your data. And so then today, what are to be focusing on is the sample preparation and data acquisition stages. So we'll start with a look at sample preparation. And it's actually quite an important thing to talk about with atom probe, because atom probe, it has very unique requirements for samples. And because of that, the sample preparation step can often be the crux of the whole experiment. And when it comes to saying, what is an achievable atom probe data set, what can you get easily, what is almost impossible, that can oftentimes be limited by purely how can you actually prepare your sample. Well, to talk about atom probe samples and what their requirements are, we have to step right back to talking about field evaporation. So field evaporation, as I mentioned earlier, is the presence of the atoms to ionize in the presence of a strong electric field. Well, how strong an electric field? What we actually need for most elements is an electric field in the order of tens of volts per nanometer, which is very high. So it's difficult to get that field strength, onto your material without forming, say an electron beam backwards from your counter electrode. So to really get that field strength concentrated on our sample, we need a little bit of a contribution from the sample itself. And we get that through its shape. Since we see as from the equation on the bottom there, the electric field strength will be essentially proportional to the applied voltage, but inversely proportional to the sample radius. So by making our samples very fine, nano-tipped needle, we can get that field strength to the levels that we need to get field evaporation to occur. So to put some numbers here, typically we'll want an atom probe sample about the size of 100 nanometer diameter or so, plus or minus a little bit. Which, to put in perspective, if you consider a human hair as being about 100 microns, it's about 1,000 times smaller than that. And so really forming this fine nanoscale needle, it's a hard requirement for atom probe analysis. And that can be where a lot of the difficulties in preparing your samples can come from. How do we actually make this fine needle out of our sample? And how do we get the material feature of interest that we're after on that needle? How do we get it? How do we make a needle out of that? So the number of ways you can make atom probe samples are quite varied, especially if you want to get into some more exotic, sample materials. But what I'd like to just talk about a little bit more are the two most common methods, that being electropolishing and focused ion beam, which really, if you consider TEM sample preparation, is kind of the same thing. You get a lot of samples prepared through either electropolishing or FIB. But as you'll see when I go through to explain it, after that, it varies. It's quite different preparing an atom probe sample from a TEM sample. So first, let's talk about electropolishing. Now, electropolishing is exactly what it sounds. We're basically trying to, selectively kind of dissolve away some of our material until we can form this nice nanoscale needle. So what we usually do is start with a material we refer to as a matchstick. So we will form our material into a little bar about 0.5 by 0.5 millimeter cross section, and then about maybe 10 millimeters long. It's not really that important, the length. And you can form this, in a variety of ways. Usually fine grinding, or a precision cutting saw will do the trick. So we'll take our matchstick and we'll set it up, and we usually use a two-stage polishing. So the first stage on the left, which we call the rough polishing, We set it up with a concentrated electrolyte solution, usually a perchloric acid-based solution, and connect it to our power supply, put our counter electrode in the solution, and then we basically will dip the sample repeatedly into the electrolyte. And what happens then, of course, is that since the very tip of the sample is being exposed to the electrolyte a little bit more than the, up the shank of the matchstick, it will begin to taper. And we basically repeat this kind of dipping process until we formed a nice taper, our matchstick into a little point. Now, this doesn't get us to the scale that we need for atom probe analysis, usually just because the material removal rate is too high using this concentrated electrolyte. So once we've got our sample kind of nicely tapered down from the original matchstick, we need to go to that second stage polishing. And this we call the microloop polishing. So in this case, we'll take the sample and usually we kind of will mount it into a crimped copper tube or something like that, just so we can handle it a little bit better. And we switch the electrolyte to a much more dilute electrolyte solution. And instead of using an entire kind of beaker of the solution, we actually will only electropolish with one drop at a time. So you can see from the schematic on the right, we basically can have one single drop of electrolyte and we suspend it under an optical microscope in a wire loop. And that loop will also serve as the counter electrode. Then we can basically move the sample in and out of that loop, usually using the stage controls on the optical microscope. And by moving the sample in and out of the droplet, be able to kind of craft that, that tip down to the scale we need for atom probe. So showing it a little bit more clearly here, that image in the top center is a view from the optical microscope. Looking down, there's no droplet in that loop right now, but you can see the wire loop and then the sample going through that. And the process is shown a little bit by the schematic on the left. So we basically want to introduce the sample actually all the way through the droplet so that most of the polishing will actually be occurring at the meniscus between the droplet and the sample. And so by moving the sample and moving where that meniscus is on the far side of the sample where it's sticking through the droplet, we can kind of sculpt that tip down to that fine scale that we need for atom probe. And really, when we get down to the scale, that kind of atom probe scale, of course, we can't see that with the optical microscope. It's much too small. So we just kind of have to trust that if we see it taper kind of into nothing and we, to the point where we really can't even focus on the fine tip anymore, we have to trust kind of that we've got it down to the size we need. But of course, if we put it onto another instrument like an SEM, as we see here on the bottom right, we can image the tip. And you can see we've got a nice taper on this sample going down to about 100 nanometers diameter at the very tip. So that's electropolishing, but more and more now, especially at the CCEM where we have multiple fibs and we have these facilities, we end up making samples using the focused ion beam. So I'll go through the process for kind of a very standard lift out, which is kind of an ex situ lift out for making atom probe samples. But usually, depending on your exact sample and what feature of interest you're after, your fib technique might have to vary a little bit from what I'm explaining here. Also, the initial condition of your sample might affect that as well. So if we were to just be doing, kind of a very standard ex situ lift out for atom probe, we'd start, as we see in the image here on the top left, we'd start by putting down a protective layer, a protective deposition, usually platinum or tungsten. Then we begin milling away the material underneath that. So we see there on the images in the top center and the top right, we begin doing undercuts with the fib at an angle until we form essentially a cantilever bar that has a tapered point essentially underneath. So it's kind of a rectangular prism, sorry, triangular prism. And then what we'll do is we'll introduce our micromanipulator, attach it to one end, as we see in the image in the bottom left, then cut the material free. So now we can extract that cantilever of material entirely. So now what we need to do is we can take that material and we can mount it onto pre-sharpened posts. So usually we'll introduce a pre-sharpened tip of usually either silicon or tungsten, sometimes copper. And then we will use the deposition in the fib to attach the end of that cantilever to the tip of these pre-sharpened posts. And so we'll do the attachment there, and then we'll cut away the material that we just attached. We'll cut it free from the rest of the cantilever. And then by doing this, we can repeat that process. So we end up attaching and cutting and attaching and cutting until we've used our little cantilever lift out to make several different tips. We've put our sample onto several different pre-sharpened tips. So people say that this is kind of like the Toblerone stage. So our cantilever, it's kind of like the shape of a Toblerone, like an upside down Toblerone bar. And just like how with a Toblerone, you break it off piece by piece. That's kind of what we do with this sample too. So typically what we would mount it on would be these silicon coupons. And these are basically manufactured to have multiple pre-sharpened tips on them. And then basically we can just, usually one lift out will fill an entire row, so about 5 or 6 tips of this lift out. And then we can introduce this coupon on this little clip that we see at the bottom left, and that can go right into the atom probe. So then, we can analyze each one of these tips. It gives us a little bit of kind of high throughput. So we're able to make a batch of tips for every one of our lift outs. But of course, attaching our sample, to the end of these little posts, it's not all we need to do. At that point, we've attached about 2 microns of material, and so we need to get it quite a bit sharper than that to run it in the atom probe. We do that through milling again on the fib. So if we look, as the image on the top left, at a section of this cantilever attached to the silicon post, we see that triangular kind of cross section with the protective layer on top and the material on the sides. What we'll do is we'll take that and we'll turn it towards the fib beam. And then we'll begin basically cutting away, usually using an annular milling pattern, until we get this material down to the scale we need. So we'll typically run these annular milling patterns, at high voltage, using smaller and smaller fib currents, and finer kind of annular inner radii, until we get down to a pretty fine scale, like we'll see there on the top right. But a stage at which, we would still have a little bit of the protective material left on top. And as you can see, that's width is maybe 250 nanometer. So we're not quite at the scale that we'd want for atom probe yet. Then what we would do is we would switch to a low kV fib beam for the final kind of sharpening and cleaning stage. So then we see on the bottom, what we can do is with the low kV fib, and running a fib at low kV, it's kind of a little defocused. So we just kind of mill it over the entire tip. And then what will happen there is all that remaining deposition material, the tungsten and the platinum, will begin to be milled away, and the tip will kind of collapse into a nice point. We can also then use this stage of milling to move that tip apex down, a certain amount from the material, from the surface of the original material if we'd like. So we can see how kind of before and after the low kV milling, we are a couple hundred nanometers diameter, we have some of that deposition material on top. When we do the low kV milling, we're milling the material away, we're removing that deposition material, we're forming it to that sharp point, and we're also removing any type of, or a lot of the damage that might have happened from the high kV fib milling onto the sides of the sample and so on. And what we end up with is a sample, like shown there on the bottom right, and I've brought the scale bar a little bit larger to make sure everyone can see it. Where we have, a very fine point, a very nice taper to our sample, and we're definitely now at the scale, where we can begin field evaporation in the atom probe. So that's, in just comparison then between those two methods, it kind of works out where basically the pros of one are the cons of the other. So the pros for electropolishing is it's fast. You can make samples pretty quickly. It's also fast because you usually don't have to, wait in a queue for your fib time. It's also inexpensive, instead of spending money on the fib, using that instrument, you are basically just paying for lab time and electrolytes and stuff. It's also a process that's very easy to repeat. So basically, if you have your sample, your electropolished sample in the atom probe, and you run the sample until it's blunt or fractured or whatnot, and you want to just repolish it using the microloop, it's very easy to then form another fine point, a few hundred microns back from the original point. And given that with atom probe, you're only evaporating a few hundred nanometers of material, moving a few hundred microns away on your electropolish sample is almost like taking an entirely different sample. So easy if you want to get a lot of repeats, do systematic analysis with a lot of different conditions and so on. Whereas with FIB, since we're only extracting a small amount of material, a couple microns that we're putting on the tip, and then we're sharpening it down to be even smaller than that. If we do have a fracture, the specimen is pretty much gone. So, you get as many repeats as samples you make with your original lift out. However, the FIB has some major advantages, and these advantages are really why it's the more common method that we end up using at the CCM to prepare our samples. The first big advantage is the FIB works with multi-phase materials. With electropolishing, it's really only suitable for metals, and they have to be fairly homogeneous even at that. You can't have, say, particle inclusions that electropolish at a highly different rate than the matrix material. But with FIB, basically, as long as the FIB beam can cut it fairly evenly, you can make a pretty even sample. I could probably get caught up on that, but for most cases, multi-phase materials work very well with the FIB. You can still make a nice tip. The FIB is also suitable for nearly any material type. Not every, but nearly any. Oxides, semiconductors, so on. Whereas really with electropolishing, it's again mostly the domain of metals and metallurgy. Then the other huge advantage of the FIB is that the FIB can give you site-specific work. So basically, you can target material features of interest throughout your microstructure. Whereas with electropolishing, you're ending up with essentially a random sampling of your material. Since, of course, with electropolishing, we can't even really see the tip that we make. But with the FIB, you basically have the choice, first off, in where you take your lift out. So, you can say, I want to look at a crack or an interface or a grain boundary, even a specific grain boundary, maybe one you highlighted from EBSD. And you can lift that out, that specific region with the FIB. And then when you're doing the sharpening stage, since you're still imaging with the SEM, it gets a little bit trickier, but you, of course, can still do it. And you can sharpen it so that that tip apex is right at your feature of interest. So if I step back a slide just to show again this stage where we look at the low kV milling on the bottom there for the FIB. Since you can use that low kV milling to kind of move, where you want that tip apex, if you keep milling it, that tip apex just gets lower and lower as it continues to mill away. So you can bring, your feature of interest in your material, let's say, a boundary, an interface or something like that, and put the tip apex right above that. So you can make sure that that site-specific feature is in your atom probe analysis volume. Then finally, the tip quality you get from the FIB is usually quite excellent. There's the possibility of some damage and a little, maybe some ion implantation, but usually we run past that in the atom probe anyway, and that's just on the material surface. Whereas with electropolishing, the tips are usually a little bit more blunt and maybe a little bit of an oxide layer from exposure to the polishing solutions or so on. But usually with FIB, you end up with much sharper tips as well. So really, if you're thinking about potentially starting up an atom probe experiment, you do need to think about, about how you would make your sample. And you have to start by kind of saying, at the very end, what do you want as your region of interest? What do you want to analyze? And then you need to kind of take these steps back and think, okay, well then, how can I make a tip out of that? Do I need to be site specific? Am I going to run into problems with multi-phase materials or so on? So there is a lot that needs to be considered with specimen preparation. This is really just kind of scratching the surface of it. Because like I said, I like to stress again, this sometimes really can be the crux of the whole experiment. Let's say we've been successful in fabricating our tips. And we'd now like to move on to the data acquisition stage. So we're going to introduce our samples into the LEAP, get them into the analysis chamber and start some of that field evaporation. So this is the control view of the local electrode atom probe. And I'm going to kind of use this to just give us an idea of what we're doing with our samples as we're loading them into the atom probe, because it gives a nice little schematic showing it. Now, this is for our model LEAP at the CCEM, but like I said, most atom probes these days are the local electrode atom probe designs, and there are some that differ from our 4000 XHR, but in the kind of broadest sense, a lot of it will be very similar. So if you're able to understand this system, you can probably very quickly adapt to a different one. So in the atom probe, there are 3 different vacuum chambers that our sample will essentially have to move through, and that's to, of course, keep the instrument in its kind of UHV high vacuum state. So the first of these is our load lock chamber, which is a small chamber with a dedicated turbo pump closed off by a gate valve from the rest of the instrument. And this is the sample this is the chamber which is the only one that will ever see atmospheric pressure, ideally. So this is the chamber that we would vent. We would load our sample into it, close it off, turn that turbo pump back on, and then basically wait until we reach an appropriate vacuum level to move the sample through. We typically like to wait until it hits, maybe the -8 scale before we move our sample in. All these numbers, by the way, these vacuum readings that we see on the chambers are in torr. So, and the time it would take to pump down, it varies a little bit depending on how many samples you're putting into the atom probe. If you're just putting in, one clip with a fib coupon on it, that won't take as long to pump down as if you put in 6 different electropolish tips. The electropolish samples sometimes will take a little bit longer to pump down just because they can be a little bit dirtier. But once we have our sample to an appropriate vacuum level, we can then move it into our buffer chamber. So we'd open up that gate valve and we'll transfer samples through the atom probe using these transfer rods. We've got 2 of them. And the transfer rods are magnetically coupled to the outside, which allows us to operate them from the outside manually into the UHV. So we'd introduce our sample into the buffer chamber. The buffer chamber not only serves as kind of a buffer in between the analysis and the load lock, but we can also store some samples in there. We store some kind of calibration materials as well. And it's not a ton of room for sample storage, but it is, we can store active samples, sharpened tips, in between analysis runs and so on. And that way we make sure that the samples that we've made, aren't seeing any more exposure to atmosphere than necessary. So, it's an ultra high vacuum environment, so it should keep the samples in pretty good condition, between runs. So then when we've got, our sample and we're ready to put it, to begin doing an experiment on it, we'll introduce it, to the analysis chamber, again, moving it using another transfer rod and behind another gate valve. Now, the analysis chamber usually sits at an order of magnitude vacuum level higher than the buffer, and that is due in part to the ion pump that's on the analysis chamber, but also the fact that we have the cryo head going into the analysis chamber. So the specimen stage itself in the atom probe will be cooled down through a closed loop helium cryo head to anywhere between about typically, maybe 20 to 80 Kelvin will be the range that we would run. In this case, as you can see here, I've got set it up to, a balmy 47 Kelvin. And that's basically to keep the specimen cooled down so that, field evaporation is, again, as controlled as possible. Those atoms are kind of locked in position and we're not having too erratic of evaporation when we go to start it. So in the analysis chamber, this is what our view would be. Of course, this is a camera view from in the analysis chamber, and in our model at Atom Probe, at least, there is no physical viewport into the analysis chamber because since we'll be firing the laser into this chamber, we of course don't want it to go out into the room, reflect into the room in any way. So we can see the sample, and this is an electropolished needle. It's crimped in a little copper tube. It's held on the sample stage there. And what we do is we need to line that up with the counter electrode. So the counter electrode, this local electrode, is basically a kind of a hollow metallic cone, a little foil cone with a very small aperture opening. And we'll basically line up our sample right to that aperture. So we'll create the field there, and then we'll have the sample. That'll create basically the area where we'll have the field evaporation occurring. Now, just to show a little bit more view of the local electrode configuration, we can see, and again, this is kind of the basis of a lot of these modern atom probes, the local electrode configuration gives us a nice high field of view, and also It allows us to concentrate the field very well at that exact tip. So as we see in that graph on the bottom left, if we're talking about the position of kind of the nearest flat surface to the tip, we can see that, once we get it even about 100 microns away from our sample tip, we find it's not really affecting the electric field generated at the tip anymore. And so that big advantage is allows us to work with microtip coupons, as I showed previously. So we're ready to start our experiment now. We've got our sample lined up, and we need to get field evaporation occurring. And so talking a little bit more about what that is. So again, field evaporation is where we want to have a surface atom ionized, desorbed from our material. So if we take us all the way back to first year material science, we can consider the potential energy curve, of an atom on in place, equilibrium position on the material. So we can see it on that blue curve in the bottom left. And we can see there that basically the shape of that potential energy curve gives a little potential energy well that'll dictate the kind of equilibrium position of that atom. And we see from the dashed curve at the top, the potential energy of an ion is going to be much higher. And so the energy barrier to actually, form an ion kind of spontaneously is so high, it's basically never going to happen. But as we bring in the presence of the electric field, the potential energy curve for that ion will drop down until eventually it approaches the potential energy curve of the material, and we end up with a very low energy barrier for evaporation. Now, since we're at cryogenic temperatures, but we're not at absolute zero, of course, so those atoms are still moving, and an atom can be considered to be kind of vibrating, and it'll be moving about within that potential energy well. So as the energy barrier for ionization gets lower, there is a chance then that vibrations of that atom will cause it to pass that energy barrier, ionize, and then desorb from the material. And it's important to know this because then you have to really consider that field evaporation overall has to be looked at as a probabilistic process. Whereas when we increase the evaporation, or when we increase the field, we're increasing the likelihood for evaporation from the different atoms. But since we're still we'll have that atom vibrating on the surface, we still have to say it as more of like I said, it's a probabilistic process. So we're going to get we need to make it more and more likely, for atoms to evaporate rather than set values. This is especially true when we consider that when we're evaporating on our entire atom probe tip, we might have varying levels of potential energy for different atoms, depending on things like their elemental identity, as well as their configuration on the surface, if they're surrounded by close packed neighbors or on an edge or so on. So overall, when we're running our experiment, we have to think about the field evaporation as kind of a threshold, but again, just kind of a probabilistic threshold. So kind of below this threshold, we're very unlikely to have evaporation. As we move beyond this threshold, we're more and more likely to have evaporation. And so we see kind of schematically here, this on the top right, as where this threshold would lie, if we consider relative field and temperature. And where we want to kind of put our sample, on this schematic would be somewhere here. Close, we want to put it at a field close to this threshold, but not over. So at a given base temperature, we would raise the DC voltage onto the sample, but we wouldn't bring it, actually to the point where we would have lots of spontaneous evaporation. And that's, of course, because we want to control the evaporation. In order to do our measurements properly, we need to time the evaporation events with our pulses. So we would bring the sample to a condition that's very close to this evaporation threshold, but we would want to move it over the evaporation threshold only briefly during our voltage pulses or during our laser pulses. And even when we do this, we're only moving it over to a condition where, it has a very small likelihood, but still a higher chance of getting an evaporation event to occur. So we might want to say maybe only have 1% of our pulses actually deliver us an evaporation event, which sounds slow, but then we pulse at a very high rate to make up for it. So this is just showing schematically, the differences here between a voltage pulse and a laser pulse. But I'd like to talk a little bit comparing the two and what we might want to choose from our experiment. So voltage pulse was kind of the original for the atom probe. Laser pulse atom probe was developed a little bit later. Voltage pulse has a few advantages. It's a lot easier to align the specimen. First of all, you can basically only have to align the specimen with the local electrode aperture. Also, the evaporation mechanisms are very straightforward. They're much more understood than the kind of like the schematics I was just showing on the previous slide. With laser pulse, it's a little bit more difficult to align, not that much more difficult, but you do have to align the laser onto your tip to get evaporation and focus it and so on. And even during the course of the experiment, you'll have to usually, you'll have to run systems to make sure that the laser keeps track of the position of the tip and stays focused on the tip. So a little bit more complication there. The interaction also between the laser and the sample is a little bit more complicated and definitely beyond the scope of this talk. But something you do have to keep in mind when working with your data. There also is the chance of getting increased surface ion migration under the laser illumination, just giving those surface ions a little bit more energy so they can maybe move positions in some cases. But laser pulse has a few major advantages. It has an increased mass resolving power, typically compared to a voltage pulse. And this is primarily due to the widths of the pulse. The laser pulse ends up being a little bit sharper than the voltage pulse. And as a result, there's a smaller window where the material will be kind of above that evaporation threshold where you will be getting ionization. And this smaller timing window corresponds then to more focused time of flights and sharper peaks on our mass to charge ratio spectrum. So a little bit better mass resolving power. Laser pulse also tends to be a little bit more gentle on your sample. You're less likely to fracture it. The electric field that we're putting the sample under an atom probe will cause a stress on the material. And when you're pulsing that field, in addition to the static DC field, you are putting an additional stress onto the material. The laser pulse doesn't have that, so it tends to be a little bit more forgiving to samples that are very brittle, very fragile, and might otherwise fracture under too high of a stress. Then the other major advantage of laser pulse is that it can really, it can work with non-conducting and semiconducting materials very well, whereas voltage pulse is primarily limited to conductive materials. Of course, you will kind of begin to suffer in terms of your data quality, if you're running with, insulating materials, even if you're running them in laser pulse mode, but you will still be able to get reasonable data, as opposed to the voltage pulse mode where you may not. The laser pulse also gives you a little bit more flexibility because it's working on an entirely different axis than the DC voltage. So whereas the voltage pulse is correlated usually to the DC voltage and running as a percentage of that DC voltage, the laser pulse allows you to, it completely decouples the DC voltage from the strength of your pulse. So it gives you a little bit more flexibility if you need it for difficult samples when you're running your acquisitions. So I just want to talk really briefly about detection of an evaporated ion. I won't want to go into too many details, but I do want to describe one thing, which is the microchannel plates. So the microchannel plates are there to serve as basically amplify the signal of a single ion, which might just be in a 1+ charge state, essentially only 1 electron's worth of charge, into an electrical signal that we can actually measure. And so it does this by basically converting that single ion impact when it enters into one of these little channels in this kind of honeycomb structure. And these microchannel plates are biased in such a way that it can convert that ion impact and then into an electron cascade that we can measure with our delay line detector. And it's important to understand how that microchannel plate works because we have to then consider, well, what happens if an ion doesn't enter one of these channels? What happens if it just impacts the surface? And the basic answer is, well, then it won't trigger an electron cascade and it won't trigger our detector. So it won't be detected at all. And therefore, this really defines, is the major factor in defining the efficiency of the atom probe. So with atom probe analysis, we're always going to be evaporating every atom. All the atoms are going to come off the material, but not all the atoms are going to be detected. And the main limiting factor there is then the open area of these microchannel plates. So depending on the local electrode atom probe model, this varies anywhere from about 56 to 86% open area of these microchannel plates. So not all of the atoms are going to be detected, But luckily, this doesn't bias our measurements in any way. It's essentially can be thought of as a random process. Does it enter one of these channels upon evaporation, or does it not? So we can expect that there's not going to be any discrimination between which atoms on the mass spectra are picked up and which of them aren't, and therefore our composition measurements and so on should all still be okay and affected uniformly. We do, however, have to keep this in mind when we go to the reconstruction stage, because we have to account for the lost volume of these undetected atoms. Finally, I'd like to also mention a little bit about what happens when an atom is ionized and is flying out, because there's a couple different models of atom probe. Can either be done with a straight flight path or a reflectron. The straight flight path is exactly as it sounds. It gives an advantage of a higher field of view at the expense of a little bit worse mass resolving power than the reflectron. The reflectron, it gives us, it essentially works by curving the flight path of the ions, which means that ions with slightly higher energies will take a slightly longer flight path, and therefore it kind of time focuses the time of flight. And this gives us, again, sharper peaks and a higher mass resolution. The main downside to the reflectron is a reduced field of view and a lower efficiency, because there is a mesh in there to create that electrostatic field for the reflectron. So again, the possibility of ions impacting it that then will be counted in our final detector. So when we're actually running the atom probe experiment, what are we controlling and what are we inputting into the data? So this is a view of the acquisition control in the Leap Control Center. Here, I happen to be running a, looks like an electropolished sample in laser mode. So there's a lot going on the screen. I just want to kind of go through a couple of the very quick, different parameters, different control parameters and experiment metrics and so on. So first of all, just showing some of the basic control parameters. First one I talked about is just basically the DC voltage. So we've mentioned that a few times already. This is just the static voltage that we're applying to create the field at the tip. And this is all about bringing the sample to the point where we're close to the kind of evaporation threshold, but not over it. And this will get varied, as the experiment continues. We can also control the pulse energy or the pulse fraction, depending on whether we're working with laser pulse mode or voltage pulse mode. In laser pulse mode, we're talking about in terms of energy delivered by the laser, so picojoules or nanojoules. And with the pulse fraction, we're describing it usually as a percentage of the DC voltage that we'll be putting onto the material. We also have the pulse rate. Typically, we would run the pulse rate, maybe between 100 and 250 kilohertz for a sample, but we can really expand beyond that. You can go a lot lower, 50 kilohertz. Some atom probes can even go up to megahertz. Overall, there's not too much of a difference for different pulse rates in most cases. However, one key thing that you have to consider is that the pulse rate will determine the maximum detectable time of flight. Because since we need to detect the time of flight correlated between the pulse and the impact on our detector, if we make our pulse rate so high that we don't give enough time for an ionized atom to fly out and hit our detector before starting the next pulse, we won't be able to essentially detect it and correlate that impact with anything. So if you're looking at essentially very slow species, very high mass to charge ratio, usually either like molecular evaporation or very heavy elements that ionize in the low charge states, like lead, for example, you'll need to run at low pulse rates to detect them. Also, if you're running a sample at a very low voltage, because that will affect the time of flight, if you're running at a very low voltage, you might need to then also drop to run at a low pulse rate in order to detect your full mass spectrum. We also have the detection rate, which you see as a percentage. Usually would run maybe 0.5 to 3%, sometimes down to 0.1%, sometimes up to 5%. And this is a percentage of pulses which deliver a evaporation event. So, we'd say, okay, we're pulsing at 100 kilohertz. We want 1% of those pulses to give us an evaporation event. And the detection rate is a target. It's we try to achieve that detection rate usually by setting up a set pulse energy or pulse fraction, and then varying the DC voltage to achieve that detection rate. So then as the experiment kind of goes on, we would change that voltage as necessary to always keep that target detection rate. And finally, we would want to put in our stop conditions. We could usually make the run end at a set time, an ion count, or a set voltage. Also, we see here some experiment feedback. We've got some imaging of the tip. We've got some orthogonal cameras there on the bottom. We've got the UV camera on the right. And then on the far right, we see some of those graphs where we're looking at the laser tracking, which of course only for laser pulse mode, where we're basically tracking the position of the laser in X, Y, as well as Z, which is its focus. And we do that by mapping the evaporation rate with respect to position. Finally, we also have the acquisition control scheme where we can look at some live feedback, from the experiment. And there's a lot of information going on here, but the most important thing to keep in mind is really this is just the information used to run the experiment. This is the information that we would use to, want to change our experiment parameters in any way. The real data, that we would want to look at for, our actual scientific, objectives would come from the reconstruction later on. So we see in the top left the detector event histogram, where we have our basically images of where the atoms are impacting our detector. I've shown a little cutout image there showing that basically this is just the projection through this of the specimen atoms through the local electrode aperture. So we align that up to fill the window, but what we're defining there is the edge actually isn't the edge of our sample, it's just the edges defined by the local electrode aperture. We also see our mass spectrum below there in the bottom center, that kind of live feed with the different peaks coming off the sample, different peaks corresponding to the different ions. Then on the right, we see from the bottom up, a live feed of the concentration. That's defined, of course, by those peaks in the mass spectrum. In the right in the center, we see the voltage curve. So that is how the DC voltage has been changed with respect to time so that we can keep the target detection rate. And then we see that. So hopefully at this point, we are setting up our atom probe experiment. It's running well. We're generating the data at good, and all the metrics look good. We're happy with it. And once this is set up, most of the time, we can then leave the atom probe to run automated. It'll run both by increasing the DC voltage or changing it as necessary to hit that detection rate. Then it'll also be, scanning and focusing the laser automatically if you're running in laser mode. And then, it'll be able to take its time to acquire, all the data that you need. But, of course, at some point, the atom probe experiment has to stop. So we need to consider, well, what happens to the end of an atom probe experiment? Well, hopefully, in the best way that atom probe experiments will end is you'll be watching that live data coming in, and you'll see that you've already collected your ROI. Let's say you've passed into your second phase and you wanted the interface, so you're happy and you just stop the experiment and you're done, and you can take your data and go on. But if you were just to leave your atom probe experiment running, what are the factors that limit our ability to generate more data? And the first one is basically that our specimen might just become too blunt. So we've been talking again and again about how a smaller, you need this really fine tip radius to be able to get field evaporation to occur. And of course, since we're actually removing material from the sample, on any tapered sample, as we do that, we'll be increasing the radius of the tip. So eventually, we account for that by increasing that DC voltage, but eventually we are going to be basically not able to hit the field strength necessary for field evaporation anymore. We will just max out the ability for the atom probe. So our sample might just end up being too blunt. Also, as we increase the voltage, we are increasing the likelihood that our experiment will be ending in the other way, which is specimen fracture. The atom probe is a very extreme environment. We're running a sample, we're putting it into, at cryogenic temperature, ultra high vacuum, we're running it in a very high electric field to the point where it's being ripped apart, and we're even blasting it with a laser and in some cases. So we're running a very extreme condition. We want to pick apart our material. We essentially want to destroy our sample. Sometimes the destruction happens, a little bit out of our control. There's a few different theories of exactly what causes atom probe samples to fracture. The most common one is that basically you'll have brittle fracture due to the electrostatic stress on a sample. That'll be followed by then, a sharp feature which can lead to a large ion current and arc backwards from the local electrode, which then melts the tip and destroys it instantly. As we see here, the image I have on the bottom right, where you can see what remains of a silicon micropost after a sample fracture. You see that it's essentially been melted and nuked by this arc. So hopefully, before a fracture occurs, you've got your data, and but if you don't, then that's why usually we just do repeats, not only to confirm our data, but to make sure that we get our data and we get good yield before without getting these sample fractures. One of the reasons why we'll always do these kind of series of tips whenever we do a fib left out or stuff like that. So once we have our data, then we would move on to the reconstruction stage. And that unfortunately is where I'll be ending the talk for today. So in summary, what we've done today, just on the experimental side, we saw that basically an atom probe experiment involves successive ionization of surface atoms, and it works in the process of field evaporation, which requires that samples are in the form of nanoscale needles. And we talked a little bit about how we can fabricate samples into that needle shape. Then we talked about how the experiment works by combining a static DC field with either a pulse or a voltage or laser to very delicately evaporate our sample atom by atom, where we detect them with a position-sensitive XY detector, and then use time of flight and evaporation sequence to be able to then get our data that we can reconstruct, knowing that we're not detecting all the atoms. We can basically run that until we either have a specimen that's too blunt or until we fracture the sample. And so then maybe in a future webinar, what we might see would be the, talking about reconstruction, talking about things like mass spectra and ranging, radius evolution, spatial calibration topics, and also looking at analysis, different ways we can analyze reconstructed data, what our capabilities are and what our limitations might be. So we'll see if we can get to that at some point. And so finally, just before I'd like to kind of switch out to the questions, I just want to highlight some references and sources I've used to get, as well as some images and stuff that I've grabbed for this talk. These are 3 texts that I have listed here. They're all very good, and they cover a lot when it comes to atom probe, and they also come to the they also go in depth on a lot of topics, as well as having references to literature on their own. So I think they're all available online, if you can look at them through your institution. So I'd highly recommend checking them all out. Also, you can go to the Kamika website, which is the manufacturer of the local electrode atom probe, and their website, atomprobe.com. They do have a lot of free resources available, so you can check that out as well. And then finally, I'd just like to thank you very much for joining us on this webinar.